Alright, so in this video we're going to do a second track that will give us a sense of how the rotation of this object is changing. So we'll go back to the first frame, and now instead of tracking the red spot in the middle, so I'm just going to make this one invisible so it doesn't get in the way. It's still going to be there, but I'm going to temporarily make it invisible. We're going to track this black spot that's on the rim as it moves down. So we're going to create a new point mass, and we'll call this one rim of disk, and this one we're going to track. So all we need to do is go straight into tracking it. So we'll just click here, and we'll keep clicking on this black dot now. So now we've tracked the motion of that, and you can kind of see that that's kind of a complex motion. So if we watch this now play, you can see that it's rotating about the center, but it's also moving down. We want to know only about the rotation, and there's a trick that we can use to find only the rotation. So if I go back here, if I click on the rim of the disk, in fact not the rim of the disk, if I go to coordinate system and I choose as reference frame the center of the disk, and I'd make this visible, you'll see that it'll shift the 0 point so that it's always the center. That way, if I look at how this rim of the disk is tracked, it's going to look only at the rotation about the center of the disk. So I've basically changed to a moving reference frame, which means that the second track here is now only looking at how the point that I've tracked is rotating about that center. So now we can have a look at the rotational motion of the disk about its own center. So if we go to, for example, in fact I want to change to, because by default it's set to degrees. So if I go to coordinate system and I click on units, I can change it to radians here. And we want to do all of our rotational calculations in radians, so that makes much more sense. Okay. And now, for the rim of the disk, I can look at the angular velocity, and we can see that the angular velocity increases with time about this center that I've defined. We can also look at the angular displacement, so rotation angle. You can see the rotation angle, it starts off rotating slowly, so the angle changes quite slowly, and then it increases until it gets quite quick at the end. Okay, so in fact for the rim of the disk I want to tell it the radius as well, so I'm going to define that. In fact I'm going to define both the mass and the radius for this as well. So the mass was 0.487 and the radius here was 0.07575. And I can now also define, in fact before I do it, we want to know what the angular acceleration is, because that's going to help us determine what the torque is that's acting on it. So if you go to angular velocity here, and we can do the same thing that we did before, because the gradient of this is how quickly the angular velocity is changing. So the gradient here is delta omega over delta t, and that is our definition of angular acceleration. So if we go to view and we choose data tool, and we can choose analyze and curve fits, and this pink line now, the gradient should be the angular acceleration. So you can copy that and then get the information that you need from that. Okay, so we want to know also how the rotational kinetic energy is changing. So to do that, we can't just click on kinetic energy because that's not defined properly. So we're going to define a new function under data functions, and we're going to call this rotational KE. And the expression for that is going to be half I omega squared. We don't yet know what I is, but we do know it's a solid disk, and we know its mass and its radius. So half I omega squared is 0.5 times I is half mr squared. So we can say 0.5 again times mass times radius squared. So this bit here, that is the rotational inertia of the disk, and then we can go times and omega squared. So this is now half I omega squared, which is the expression for the rotational kinetic energy. And we can have a look and see how that changes. So we can see that that also increases, and we end up with just over 1 joule of rotational kinetic energy at the end here. In fact, we can watch how it changes. So as it moves down, the rotational kinetic energy increases as well. And so this will be a useful graph to include, especially looking at these final and initial points here. So you can click it and see how the rotational energy sort of changes during the motion as well. Okay, once you've gone through all of this, I recommend copying over all of the relevant images and copying over all of the data that's going to be relevant, and that's kind of listed in your worksheet, and then going through the worksheet to see how these numbers sort of come out and how we can use those numbers to show what's going on with the motion.